Bienvenue au séminaire en informatique cognitive qui est devenu un peu les séminaires en IA générative. On souhaite la bienvenue à Ari HOLTZMAN qui va parler de articuler l'ineffable. Est-ce que l'expression ineffable vous est connue? Pas de réponse. Ça veut dire ce qui peut s'exprimer en mots. Le tournant analytique de l'IA générative. Ari est professeur adjoint en informatique et sciences des données à l'Université de Chicago. Il dirige le laboratoire de conceptualisation. Sa recherche porte sur le développement de nouveaux cadres conceptuels pour comprendre les modèles génératifs, les traitant comme les systèmes complexes émergents, comme si c'était un phénomène naturel qui se faisait, et pas quelque chose qu'on vient et organique, plutôt que comme les artefacts d'ingénierie traditionnels. Harry croit que le principal goulot d'étranglement dans la science des LLM, des grands modèles de langage, est le manque de bon vocabulaire pour décrire les LLM. Il a introduit l'échantillonnage par noyau nucleus sampling, un algorithme de génération de texte utilisé dans les systèmes déployés, y compris l'API d'OpenAI même. Alors avec ça, with that, I'm going to pass it to Ari, to whom the first question is, do you want to take questions while you are giving your presentation, or I'll tell you the advantages and the disadvantages, or do you want to wait till the end? If you'll take them during the talk, you don't have to worry about running out of time because it'll all be everything will be reckoned in. Firstly, you have an hour and a half. If you take questions, you might be you might be cut off in your train of thought. So it depends how you're used to talking.
I usually take questions during, and then like if we get 10 questions at once, I might eventually say like, okay, we should cover the rest. But I kind of like during because otherwise you face recency bias and everyone asks about the last project instead of doing that. So I'm happy to take questions during.
That's good. And I want to add to that that we questions can come for the people who are far away. Simply turn on your mic and say it because I can't monitor everything. So and if it turns out that Ari doesn't want to take one now, we'll just tell you. But go ahead and ask questions.
Exactly. Just
Et,
jump in.
et- et la même chose ici. Levez la main, je vais tout de suite dire que vous avez une question et si Ari ne veut pas, on attend. Okay, with that, welcome to Montreal. I forgot to show you Montreal. Just a
I love Montreal, by the way. I keep thinking about how I might end up there in the long run. It's one of my favorite cities, so it's an honor to virtually be here, and it's an honor to be at this at this seminar to get to talk here. I'm sure all of you guys know, but like Sivan is a person who like a lot of us in computer science who think about intelligence and think about a little bit of philosophy. He opened up the world to us. He said, "Look, there are all of these questions that we really don't know how to answer, and questions we don't know how to answer kind of became my thing, and it's became my entire career. And so I'm super excited to be here. I named this talk something kind of crazy, articulating the ineffable, as you may have noticed. And so, like, let's just go through that a little bit. One second, there appears to be a slight issue. As many of you may know, the idea of the ineffable is that which cannot be expressed in words. And so it might seem like a bit of an oxymoron to say we could articulate it, but I want to argue this is actually commonplace, right? The universe is inherently indescribable. You can't win against the universe. It's just too complex. You don't have enough data. You're from this limited human perspective. And yes, we can invent measurement tools, but language will always kind of be like this man nailing the border between the sea and land into existence. There's some barrier there, but it's too fuzzy and our tools are too weak. And that doesn't mean we can't get anything done, right? Now consider my field, at least, in this interim, to be LLMs more than it is NLP. And so as an LLM scientist, I think we think about generalization and memorization. And we think about generalization a little bit differently from traditional machine learning. But there's certainly some difference. There's a difference between a language model just memorizing the test set and giving us the answers that we told it to versus generalizing to new questions. But it turns out that in order to generalize properly, there is some minimum component of memorization you need. This is not just empirical, it is theoretically true. And so this boundary is fuzzy, but it's real. And so I think I started to view the purpose of basically all human knowledge endeavors of the science and the humanities to push back the boundary of the ineffable. And by that, I mean to reveal that things we thought of were true as truly ineffable were actually just temporarily inarticulable, and we needed to kind of get our claws into them. And so an example of this in science that I think many of you are aware of is the concept of infinity. Because it used to be infinity was this high abstract concept that, people understood the idea of indefinite growth, but they didn't have a way to talk about different infinities. But then Cantor came along and gave us this Alice system, which allowed us to say certain infinities are reducible to each other and certain ones aren't, and they're in some fundamental way bigger than other infinities. And so we were able to rigorize this concept that had just been this high abstraction that could never, we'd had trouble grounding until that point. And so I'm interested in what the infinities of LLMs are. What do we make reference to without fully understanding, and that we kind of need more machinery to work with? And I think there are a whole host of possibilities right now. Hallucination, reasoning, generalization, as we talked about, this idea of alignment. I think overfitting, which is often considered kind of obvious, is really not obvious what that means in LLMs. And if you're interested, look up this really interesting paper called hyperfitting. And so I'm just here to say, LLMs are a model organism for articulation. We've had them for years, but we still don't understand so many different aspects of them. And so they have all of these neat properties that make them useful as a model articulation organism. For one thing, they're radically new because we haven't, and we know that because we haven't been able to take them apart with our previous tools. For another thing, they produce human media. So we can argue whether what they produce, is really understandable as writing or as images in the normal sense, but certainly it looks enough like media that humans produce or that cameras produce, which are made by humans, that we should think of them as we can think of ourselves as being particularly sensitive to the outputs that they have. The same way that when a image generation model creates has an image of a person, we're most sensitive to the weird ways in which they mess up the face because humans are particularly sensitive to facial structure. In that same way, we're particularly sensitive to human media like writing, and so it's very convenient that LLMs produce human media so that we can study them better. And then I want to say that we're highly measurable. They're highly measurable. And so this might be contentious, and so I'll just give you a little idea of what I mean. LLMs are highly measurable in the following sense, in which that they're easier to study than the other thing that we know that uses language, which is humans. So for one thing, for LLMs, we have a perfect fidelity state of encoding, right? You can go onto Hugging Face and download exactly the state of a language model, right? Exactly the parameters by which it computes things. And even if I can save a certain pattern in the language model during inference, right? I can save the activations of the model and carry them over later. We have complete theory of low-level dynamics in language models in that we can simulate them. And this is kind of funny terminology because by simulate a language model, I mean run inference on a language model. Since a language model is a computational construct, it is by definition simulable because running it is the same as simulating it. And these two things give us exact repeatability. In any language modeling experiment, we can design it such that it's exactly repeatable. Now, people don't always do this. We use hardware that allows for indeterminacy to get into the program. But if we want to, it is always on the table to have exactly repeatable experiments. Whereas with humans, it is just completely not on the table to have exactly repeatable experiments. It is simply impossible to repeat an experiment exactly with a human being. Even if you find a new human, they're different in too many ways to quantify. This is just too difficult. So some other things that are useful are the ease of perturbation of language models. We can go in and do little micro surgeries on language models, and that is both unethical and very illegal to do with people. And even when people are consenting to, doing surgeries for, exploratory potential treatments, it's still a long process to get government authorization for that. Whereas with LLMs, there's no such barrier, and so we have a lot more freedom in how we test them. And kind of more high concept one that's a little bit funny is that LLMs don't have observer effects. So I mean something very specific by this. If you hint to a language model what the answer should be, it will certainly use that information. But what I mean by observer effects is that if I put a language model in one laboratory or another laboratory, it won't change its answer because of that laboratory. It might change it because you're running inference wrong, or because you prompted it differently. But fundamentally, if right before I run an experiment, I tell a language model, you're a good language model, and then I just reset its memory, there will be no difference in the experiment. And so this is very, very different from humans. If you look at psychology or sociology, observer effects are like half of what we're trying to compensate with in experiments. And then, as I mentioned earlier, they output human understandable media only on average. So this is no longer as true as it used to be. Things like chain of thought are arguably not human understandable media, and that's a whole nother discussion. But most of what they output is human understandable media, whereas humans have all of these other byproducts, right? Like we produce pheromones, we produce hormones. All of these things are outputs that we produce to the environment. And language models don't kind of have that same thing where they have to have outputs because of the way they're engineered. I guess you could call heat an output, but it's not as useful of a measure, and it doesn't say as much about language models. So all this is to say, LLMs are incredibly measurable in comparison to people. They're the other thing that uses language, and yet we lack the correct abstractions to meaningfully theorize large language models. So I'm reminded of this paper that I loved way back when in grad school called Could a Neuroscientist Understand a Microprocessor? In which basically Eric Jonas and Conrad Cording go and take a microprocessor and they perform cognitive science on it, right? As neuroscientists do. They literally do, little microsurgeries and lesions and things like this, and they see, could we understand how a microprocessor works by doing these operations? And as you might expect, the answer to this is no. Neuroscience tools are just not strong enough to do this. They're also not designed to deal with the regularities of a microprocessor. But since a microprocessor is significantly simpler than a human brain, you kind of hope that this would be possible, but it's not. And so I would like to ask you guys, could a computer scientist describe a language model? And I think my personal answer is no, and I want to explain why. So this is a kind of like a abstract diagram of how I think about the current transformer language models, which is that, on the top, we have the benchmark performance, question answering, summarization, machine translation, all the things that we know modern language models can do. On the bottom, we have these elements that we used to build these language models. And so we know that these are we know how these work because we designed them and that's how we built the language model. And then we know a little bit about the learned structure. So we know a little bit that like attention was built a certain way, but the weights that the parametric weights that the language model learns to use for its attention have certain patterns. But all the stuff in the middle is pretty confusing, actually. And then we have a little bit of understanding about what makes things good at benchmark performance, but kind of the intermediate behaviors are largely unknown to us. Then we have a very, different system that has some of the same outputs, like humans, right? We know humans can answer questions. We know that they can summarize things. We know that they can translate things if they know two languages. I guess it's no longer machine translation, but you get the idea. And since we know so little about this intermediate zone, we're tempted to take what we know about humans and then import it into language model space to say, hey, maybe attention in language models is similar to attention in humans. And the problem is, even though this is so, it's so seductive to try to do something like this, it usually doesn't work. Usually the parallels we draw are just so far off, and maybe they're contingent on the certain models that are happening, as with using perplexity for human surprise, right? Is kind of, it worked for a while, and now it looks like it's no longer working. So the problem is we end up with a situation where we understand kind of the top layers and a little bit more of the bottom layers. And then this intermediate kind of space of how language models work is largely unknown. And I focus on these kind of like the most intermediate representation, which I think is going to be the most explanatory of everything. I think it's going to be the most parsimonious explanation to look at where everything converges between benchmark performance and the underlying elements. You can think about it like I know humans can do all of these crazy things like make art and make calculus, and I know that they're made of molecules, but I want something in between, not at the neuron level, but maybe, do groups of neurons compute certain functions or something like that. But I want to do that for LLMs, and I want to do it behaviorally more than I want to do it mechanistically, which I'll get into later. So I think we're going to explain benchmark performance using these things. And I kind of mentioned this in the chit chat before the talk that I think we have to be very careful about trying to get rigorous too early, which might sound crazy for a scientist to say. I took this idea and the following diagram from my pseudonymous friend Suspended Reason about why we must be careful not to get too formal too early. And he uses the example of evolution, in which there was this clear pipeline from inexactitude to exactitude. So we started with people just seeing animals and having folk theories about them, right? You'd say, oh, there are kind of all of these animals that have a flat back and have four legs. Maybe they're somehow related to each other, maybe they're not. And we don't really know where birds go in the winter. Maybe they turn into fish. Who knows? Uh, and then you had these people collecting these things into books called bestiaries and herbaria, where they would just draw animals and say, hey, I saw a bunch of these animals, and these animals that people thought were different are probably all the same thing, but this one is the male and this one is the female, or this is during the winter. And then Linnaeus went around, took in a lot of this information, and said, hey, this kind of looks like a tree. He didn't say where the tree came from, right? But he gave structure to it. And then it took, that structure and Darwin looking at things around him, like pigeon breeding, to say, hey, maybe this tree structure comes from some kind of causal mechanism, which he termed natural selection, right? And it wasn't until, quite a bit later that after thinking about evolution a lot and collecting more evidence, we were able to really get the mathematics going here for something like evolutionary game theory, which now gives us very rigorous hypothesis to test. So I want to be clear about where I am on this. I'm, somewhere in this weird middle zone. You can think of me right in the middle of this box. In my greatest moment, if I manage to, transcend, maybe I'll touch the origin of species angle and I'll have a theory of the causality of some of these issues. But I'm firmly mostly in the somewhere between stamp collecting and the Linnaean taxonomy. I want to show that there's structure to the behavior of language models, and I would love to find a causal mechanism. But I'm slightly pessimistic that we can jump right to that without understanding more about the underlying structure. And so, with all of this intro said, let's talk about one of these behaviors that us in the lab have recently discovered. And this is joint work with a bunch of my wonderful students and also Chen Hao Tan, led by Harvey Fu. And it's called absence bench. Language models can't tell what's missing. And to get you to understand what I mean by absence, let's use the example of the Wicked Bible. So this is a book that was released in 1631, and it was intended to be a reprint of the King James Bible. But there was a little tiny omission. In Exodus 20:14, instead of saying, thou shalt not commit adultery, the Wicked Bible says, thou shalt commit adultery. It's just this tiny one word difference, but it made a big difference, and people didn't buy this book anymore. And I want to use this example to say omitted information matters, and language models likely wouldn't have been able to catch this mistake. That's what I mean by omission. So to test this, we took a bunch of domains, for instance, poetry, and we did the following. We basically put two copies of these documents into the context window of a language model. The first copy is complete. So for instance, this is Walt Whitman's Song of Myself. I celebrate and sing myself, and what I assume you shall assume, nature without check with original energy. Those are, there's some stuff in between, but we then omit this line, and what I assume, you shall assume. And then we ask the model what was missing. And most models are not able to do this consistently. Now, this is very much in contrast to what's called needle in a haystack, where you put a weird sentence in the middle of something, and then you ask the model to condition on that information. So, for instance, in the middle of this poem, we say the best thing to do in Chicago is to walk by the lake, and then we see if the model picks up on that information, and it absolutely does. And so this is called needle in a haystack. And models are very, very good at needle in a haystack. They have most of the modern models that you'd use, ChatGPT, Gemini, Grok, Claude. All of these models are basically above 99%, often 100% success rate at needle in a haystack, even for documents that are 100,000 lines long. But for documents that are only 1,000 or 2,000 lines long, they often can't recognize missing lines, which is pretty crazy. And you might say, that's cute, but why does it matter? But I would say, where does it matter? And it matters where we use language models. Like, let's say, you kind of have a terms of service that's missing something that should be there, or you forgot to take a certain measurement for a patient, or a code base is missing some kind of check. This would be important. For a specific example, in 2016, Google got rid of the following sentence from their privacy policy. We will not combine double-click cookie information with personally identifiable information unless we have your opt-in consent. This was a huge deal. It basically allowed them to sell user data at an unprecedented scale, and I don't think an LLM would have caught it. So trustworthy agents that are going to take action on your part, for instance, agreeing to a privacy policy, have to be omission aware. They can't just say, oops, did I miss something after the fact when it's too late. And so first things first, let's just see some data, right? Language models, all the best language models, Gemini, Claude, Qwen, GPT-4, Llama, are really, really bad at absence bench. And to give you kind of a sense of what absence bench is made of, it's made of three domains: poetry. And the reason we have poetry is actually because I found this when I was trying to use GPT-4 to help me memorize poetry. And I kept saying, oh, what did I miss? And it kept not actually getting things that I missed. Uh, and then we just added two domains that we thought were interesting. One is numerical sequences, which is kind of like the easiest possible option, right? You just have in order numbers, and then you omit some of them. And then GitHub pull request, which seems like a really obvious thing that language models should be good at, identifying missing information in a pull request. So the task kind of looks like this, just as a little reminder. You have the original document, you have the context window, and you put the original context first. Then you put the modified context, and then you ask, what is omitted in the modified context? It's that simple. There's nothing special about this. We don't train models in some weird way. We just give this directly to all the best models, and somehow this is difficult. And it's interesting, and this is kind of the thing that bothers us so much, is that omission is so much harder than insertion. And one of the reasons that this bothers us is because the computational complexity of just solving absence bench without a language model, just with Python, is linear. It's really, really easy to write a program to solve this problem. So why do models with billions of parameters underperform this code? And the answer I'm here to tell you is a little bit disappointing, which is we don't really know. We're looking more into it. But we, of course, did some studies to try to figure out what's going on. So context length definitely has a major impact. If you make it way longer, definitely LLMs perform worse. But omission also has an impact. So here, color encodes omission. And as you can see, there's something really weird going on where omitting less lines, so having more of the context be whole, is actually harder. This is crazy. This is like saying, if I basically make you retrieve less lines, it's somehow harder. And we don't really know why this is true. One theory that we have is that because there are less omissions, the model doesn't know to flag them, and it has kind of more trouble deciding what to flag. Whereas if there are more omissions, the model can kind of get used to omissions and flagging them. But this is a very intuitive theory. We don't have any mechanism, and we kind of looked into the mechanism and not found anything obvious. Another really interesting thing is inference time compute, right? Where you let the models do chain of thought and think for a while in order to answer these questions. Now, it does help a significant amount when it comes to closed source models that are way better at chain of thought reasoning. But one of the crazy things is that on average, the models need to repeat the document multiple times in order to actually solve this problem. So if you imagine a human doing this, what I would do is I would just go through the original poem and I would just see which lines are missing as I go through the modified poem. So I might need to repeat this once. But on average, the models are repeating this, 2 times for poetry, 4.5 times for numerical sequences, a little bit, almost as many as 4 times on average for GitHub PRs. So the models are going back again and again and clearly aren't implementing an actually efficient algorithm, even when we give them the latitude to do whatever they want in chain of thought, which is kind of crazy. Um, what I think is the most interesting kind of study that we did here to try to understand what's going on is what we call the placeholder study, in which instead of purely omitting the lines, we literally just added the notation missing line where we omitted a line. And this increased the F1 significantly, and it increased accuracy by like 46, yeah, by 46.8%. Um, which is a huge amount, right? This is like adding tens of billions of parameters to these models essentially in equivalence. And so the question is, wait, what? Why would that matter? If all I'm doing is just adding the word missing line, the words missing line, why is this making the problem easier? So we have a few theories about this, but again, we don't have any answers. Um, the basic hypothesis that I have is that it's a part of attention, right? That basically transformer language models are pivot machines. They pivot on information that they find. And by including the term missing line, we give them information to pivot to then look around, see what was near that, and go back to the original context to see the missing line. So the idea would be that the attention has trouble pivoting on information that's not there. And so providing a pivot, such as the term missing line, allows the model to be solved. However, it's still not obvious how to try to find this mechanism, even if we have this hypothesis, because attention is huge, right? It just produces so many activations, it contains so many parameters. It's not clear what it would mean for us to actually assert this hypothesis is true. And we have a bunch of people working on this now. And if you have any ideas, I'm all ears. But I think it's just kind of an interesting mystery and an interesting benchmark. So the upshot for me is that this matters, not just because, we want models to be good in medical context. It matters for LLM research as a whole. Because I don't know if you've looked at other benchmarks lately, but most of them use LLM as a judge in some capacity. Often they have a reference that they're using, but we have to use LLMs to judge other LLMs right now because we just don't have better metrics than that. LLMs are our best automated meaning measures, right? We just do not have better measures than LLMs. But if they're not omission sensitive, that means that we have a very biased set of errors when it comes to LM benchmarks. So for instance, I did a little toy experiment here that maybe will turn into another paper where I tried to see if LLMs would grade things highly, even if they omitted like certain parts of an assignment, and they did. And so this matters a lot, not just if, teachers are going to use LMs for grading, which they probably shouldn't, but if we're going to use LM to grade other LMs might learn to basically bypass LM as a judge in various ways that are going to be hard for us to detect. So this is also just going to have a little PR moment of we're going to make another one. It's going to be released in like a few weeks. That's even harder for even the latest models because as far as we can tell, this is just not a solved problem. And we wanted to collect a bunch more domains in order to have more to analyze. And so if you're interested in this, we encourage you to download the code, download the data, and get in contact with me if you have any ideas about how we could make things better. And this is a good moment for questions about this because I'm about to move on to another project in kind of a totally different direction. So I'll pause for 10 seconds. And if anyone has questions about Absence Bench, I'm happy to take them.
Go ahead, Dave.
Hi. Well, maybe it's going too deep into speculating about the reasons,
Go
but
for it.
when you describe,
Oh, I just said go for it.
sorry, and because when I listened to what you said, I kind of I was not surprised that the models didn't perform well on it, but at first I wasn't quite sure why I wasn't surprised, and I thought, well, it's because how I think about attention and compositionality. I don't think of transformers as really doing compositionality
Sure.
correctly. And there's like a bunch of papers on that, why they're not doing that. So instead, attention sort of compensates for the lack of proper compositional abilities by meshing words together, right? Like every token becomes a mix of all the other tokens, right? Instead of taking a thing and splitting it into parts and then composing it and so on. And doesn't that sound somewhat similar to the problem of or doesn't it sound like we need this kind of compositionality, this ability to break things into separate parts and then combining them rather than mixing them all up together for solving absence bench?
I think that's a really interesting point. I'm not 100% sure that I agree that this would solve it though, or wouldn't, or like kind of would have an interference effect because the problem is one thing that LLMs are super sensitive to is line breaks. Like for instance, there's a recent Claude paper about how like one of the first things LLMs learn is to where to like put a line break, right? And so since we do this on a line by line basis, it feels like even if they're mushing things together, that should still create basically a unique signature, and that like the model should have a unique representation for lines. And one of the things that's also interesting is that there are plenty of domains where LLMs are pretty good. So, for instance, if you just give it raw news text, it's not bad at this, right? And so, one of the theories we have is that it's related to the underlying perplexity of the text that's being, where you have to retrieve different lines. But actually, the results from that are currently mixed. We're doing like a bigger study. And so it's not clear whether it's harder for LLMs to retrieve high perplexity lines or low perplexity lines, or in high perplexity domains or low perplexity domains. So I agree that compositionality is probably key here, and that the model has some kind of heuristic in which it's like not fully understanding the information and not like reducing it into the correct representation. But it's not clear to me, like if it was all totally mixed, maybe. But since we're doing it at a line level, we're being pretty generous to LLMs about their representation, and it feels like this is a little bit crazy. But it could also be that this is the key. I don't pretend to know.
Thank you.
Great. All right. If that's all, I'll move on to LLM memory. And I'll make a pretty hot take here, which is that memory is a more important domain to think about the chasm between LLMs and people than embodiment. So many have suggested that embodiment is a thing that most estranges LLMs from humans, including me from the past. And I don't know even that I'm right about this new idea, but I've come to the idea that memory is a more influential difference. And, one of the examples I like to think about this is a lot of our thinking relies on episodic memories, which LLMs very definitively do not have. There are now a ton of papers showing that if you look at attempts at kind of putting together LLM memories where you're like, oh, do you know this thing? Do you remember this thing happening? There's nothing like that. Um, and we rely on episodic memories for lots of things that don't appear to be immediately episodic. So, for instance, if I need to remember who the Pope is, then I think about Pope Francis, and then I think, no, like Pope Francis died, and then there was a new Pope, and there was the conclave, and now there's Pope Leo. So often, even when I'm remembering something that is not purely episodic, I need episodic memory in order to retrieve it, or in order to be part of the knowledge update at least the first few times, right? And the fact that LLMs don't have episodic memory causes a lot of weirdness for sure. So for instance, one example I like is this thing I'm currently calling false memories that nobody really knows how it works. It's best illustrated with the seahorse emoji. There is no seahorse emoji. But if you ask any major LLM, at least up until last week, maybe now they've all updated and they try to paper this over, all of the LLMs are sure that there's a seahorse emoji because there was a kind of movement to have a seahorse emoji. It was a proposal given to, I forgot the body that decides the new emojis, one of the Unicode bodies. And it's kind of a common belief that there's a seahorse emoji, but there isn't one. So LLMs will try to produce the seahorse emoji, and of course there isn't one, so they can't, and they'll recognize that they're failing, and they'll go into these loops trying to reason about where the seahorse emoji is, and then they'll fail, and they often won't give up. They'll say, actually, I can't produce it, but you can look it up, right? There really is a seahorse emoji. And it's tempting to say, well, this is a problem with visualization, but even when it comes to not having to visualize a seahorse emoji at all, models are sure that there's a seahorse emoji. And I actually didn't include it here, I should have, but you can ask it about lots of other emojis where, there really isn't an emoji for that, like the dining booth emoji. And models are often pretty confident that there is no such emoji. So models have this weirdness around memory, and it's not exactly clear where it comes from. But I do want to say that embodiment probably wouldn't solve this, right? Even if models existed in the world, they would not necessarily, be able to solve this problem. I think that what actually happens here is they have to exist probably in time in order to solve this. Now, that's a big question. I'm not going to solve that. But I did want to study the mechanics of LLM memory a little bit more so we can understand what they are doing. And so we invented this technique called dynamic weight grafting in order to do that. And our motivating question is, where are relations remembered? So we often teach LLMs new facts, right? Like I talked about the new Pope. There are also new movies, new product launches. And the question is, where does that knowledge live inside a transformer? And to see what I mean by this is kind of a common story. This is from a GAVA paper in for those of you who care about information flow in LLMs and memory in LLMs, you should basically read every Morgeva paper available. She's just the best at this stuff, and maybe a little bit of Ellie Pavlik's papers. She's also amazing, but that doesn't have as much of a focus on memory exactly. And the basic view here is that when you have to remember a relation completion, right? So that Beats Music is owned by Apple, that basically when you see the first entity in the relation, you kind of enrich the residual stream of the transformer in such a way that you have a lot of information available there. And then when you see the relation, this is imported kind of into the residual stream too. And then right before the relation completion needs to be remembered, these all line up, and then you remember the completion, which is Apple in this case. But that doesn't tell us where the information about Apple is necessarily. It doesn't tell us whether, for instance, Apple was remembered here, and once you know about Beats Music, you can like extract, using some kind of probe, the information that Apple is owned or Beats Music is owned by Apple, or whether that information is only here, or whether it's remembered somewhere entirely different, or whether it's diffuse and kind of slowly gets added up. And the reason why this kind of study can't show us this is that it uses attention knockout. So attention knockout means that we look at the attention mechanisms and we just knock out certain heads, for instance, here. And then we see that that destroys the propagation and Apple is no longer predicted there. But that doesn't tell us whether, the information about Apple was remembered before that knockout or after that knockout. It just tells us that that propagation was needed, right? But there are multiple alternative hypotheses, for instance, that Beats Music creates a trigger to remember Apple, but it doesn't know about the Apple information itself. And so in order to study this more rigorously, we created a very kind of exact and manipulable set task and data scenario, right? Where it's simple relation completion. We have a subject and a relation, and then we want to predict the object. So for instance, Zendaya co-stars in a new film with, and then we're going to predict like Twiggy, for instance, from our data set. And then synthetic data sets to control exposure. So we have 3 synthetic data sets that we made to exactly kind of follow, to give this information and nothing else that might kind of give away things. So we use fake movies with real actors, fake actors in fake movies, and real movies and real actors, but they're all shuffled. And we get the same results with all of them, suggesting that our results are pretty robust. And we produce a bunch of these, and then we run a bunch of experiments. And now let's talk about the experiments. So just so that we're super clear about what we're testing here, we have 2 test scenarios that we rely on most of the time. Brad Pitt starred in a movie with, so like kind of the headline version of the relation completion, and the QA format. So who starred in a movie alongside Brad Pitt? Answer an actor named, and then X person. And it's really important to have both of these because we want to make sure that it's not just like the word with that is triggering the recall of the memory, or if it is that, we want to know that. And we want to make sure it's not just the position, or if it is the position right before the relation needs to be recalled, we want to know that. And if this is a little bit confusing, I promise you it'll all make sense once we show you some diagrams, but I'm kind of preceding some information. So we have a simple recipe in order to kind of do dynamic link grafting. We take a pre-trained model and we fine-tune it with new relations that were never seen in the training data because we made them up into an SFT model. And we do what's called grafting parts of the SFT into the pre-trained model, which means we literally swap the weights during inference. So, for one token position, instead of the pre-trained model operating, we use the weights of the supervised fine-tuning, the SFT model, but it's still getting all the inputs, all the activations from the pre-trained model. So it's really as if we grafted in the SFT model just for a token, for instance, or just for a specific feed forward, just for a specific mechanism. And what we want to find is the smallest set of parameters that is necessary and sufficient to complete the relation. Because since the pre-trained model doesn't know about the relation, if we find, the smallest sets of parameters that is necessary and sufficient to complete the relation, that is, at least that is necessary to remember the actual relation. And it gives us kind of a place to look at where LLM memory is. So visually, what this looks like is we have these 2 models represented by 2 different colors in this case. And we graphed the model, we graphed parts of the SFT model into the pre-trained model. And you'll notice, we can graph just specific parts and we can do it just for specific token positions. They don't have to be the same at every position. And most of the model is still the pre-trained model. We try to graft as little as possible. And as you can see from the results, basically, the SFT model has a certain answer. The pre-trained model has a certain answer. And what we're trying to do is make the grafted model give us the SFT answer. So in this case, pre-trained answer is considered wrong. The SFT model is considered correct. And we want to make the grafted model produce the SFT version. And it's worth noting there may be multiple sets, minimal sets of parameters, but in general, we're working at a high enough level where we don't, graft in individual neurons, we graft in individual mechanisms, so either an entire feed forward or an entire attention block. And so it's actually pretty clear what are the minimal sets. So those of you who are in the kind of more interested in the mech interp space might know about activation patching, which I'll explain very briefly here. Activation patching is where you take the same model with two different prompts, and then you basically replace the thoughts of one model with the thoughts of another model given a different prompt. So it's as if, you asked me a question like, what is the capital of France? And normally I would have said Paris, but then you graft in sorry, I shouldn't use graft. The graft should be for parameters. You kind of transfer in the thoughts of me. If you ask me instead, what is the capital of California? And I would say Sacramento. And then if you do this, you transfer in the thoughts and swap them out, then I'll say Sacramento instead of Paris for France, right? And this is a useful technique for understanding models, but it replaces the inference time information about the model, the residual stream, or the activations, as we call them. What we're doing is actually changing the actual thought, like the actual mechanism in the model. So in the human brain, this would be equivalent to changing the neurons in the model. And we are a little changing the neurons in these models, but using neurons twice is kind of confusing. So for instance, if these represent feed forwards and attention, we're actually replacing the feed forward in a model in order to graft it, rather than replacing the information produced by a feed forward in another prompt. Whereas activation process patching actually replaces the thoughts, i.e. the activations or the residual stream. And so if you ask, why not just use the activation patching to study this problem? Well, the activation patching overwrites the residual stream. It overwrites all earlier computations. So if the information was already available before, activation patching doesn't tell you about that. And it's an extremely brute force mechanism in that sense, right? It just overrides all the information, and it can't tell us if the information already existed. We want to intervene on mechanism. We want to say, what is the mechanism and where is the mechanism where LLMs suddenly remember something, rather than what is the thought that contains the information. And so this gives us dynamic rate grafting, in which during generation, we temporarily swap chosen weights from SFT into the pre-model, as I mentioned, and we can kind of do this any way we want, but we'll start with the simplest way, which is we replace all the mechanisms, so all the attentions and all the feed forwards, but for a single position. So for instance, in this case, on the relation position where it says Zendaya co-stars with Twiggy, we'll just do it for co-stars. And it turns out, if you kind of look at this for a while and you do some experiments, there are three positions that kind of matter at all, which is the movie itself, the first entity mentioned, and then the last token before prediction. So we call these MV, FE, and LT. And as it turns out, these are the ones that actually matter, and movie in general doesn't matter. There are some models where I believe it matters slightly, but it's very much weaker. And so if you look at the accuracy of relation completion, and it's worth here noting that I'm using top 5 accuracy, as in we count it as a win if this is in the top 5 possible completions. And the reason we do that isn't actually because the model gets it wrong that much, but because it often, will predict punctuation or predict the, or kind of, have a parenthesis, opening parenthesis. So it will just kind of do something completely different. And it's not trivial to make sure that we're getting the model to produce the exact token that we want in these completions, because the model has a lot of syntactic freedom since it's just a generative model that produces text. We looked at this with multiple other, top 5 versus top 10, et cetera, and it's pretty robust. So we trust this metric, but you can look at the paper for details. And basically, if you look at this, the first entity and the last token basically explain all of the behavior, right? Whereas the last token tends to actually explain most of the behavior. The first token explains less of the relation to completion, but still a significant amount. And everything else, the complement, where you just graft in everything but the first entity and the last token, every other position, basically doesn't matter at all. So we know this. And as it turns out, if you look at these two, what we call the recall pathway, where the model remembers things last minute rather than remembering them when it sees the first entity, is significantly stronger. And what we wanted to do is kind of understand the recall pathway a little bit better. So we said, can we localize behavior to specific model components, not just token positions? And we used three models to do this: a pre-trained model, a task-specific model, which was fine-tuned on relations, but not the evaluation set relations, so not the test set relations, and therefore doesn't know the answer to these questions, even though it's used to completing relations, and it's used to that kind of mechanic of, okay, given a co-star and a relation, I'm going to complete it. And then the relation-specific one, which is just called SFT before, that actually has the relations we want. And what we found is really cool. So if you look at this data, the task-specific data just looks kind of like the same relation data, but without the actual relation we want. The relation-specific data looks like the kind of like the evaluation data, but it's kind of more open, like in a new film, etc. And the evaluation data is just straight up completing the relation. And what you see is the following: that the pre-trained model, can't get this. The task-specific model can't get this, and the relation-specific model can. And the kind of way that this happens with the grafted model is that the model uses a combination of task-specific attention and relation-specific feed-forward networks. So to show you that visually, what we're saying here is that the attention in the first entity and in the last token has to actually be grafted in from the task-specific model. So it needs to know how to do relation completion, but only the very final feed-forwards need the actual information about the relation being completed. And what this tells us is that the model really is remembering things last minute. It's not kind of pre-remembering something in advance, but there's a specific trigger mechanism when it learns relation completion that needs to kind of go in there, whereas Endaya somehow triggers this information. And so the takeaways here are that attention knockout and activation patching are popular, but they're kind of blunt, right? They conflate information with mechanism when we use them for these kinds of things, but dynamic weight grafting can do better. And you might say, okay, so what? But I'll say, listen, if you want to do unlearning, if you want to do knowledge editing, well, you need to know where the knowledge is versus what is just kind of helping the model remember, but doesn't change anything. And a bigger reason why I care personally is that where information is stored is indicative of where it will be used. And I don't know if you guys have played around with fine-tuning LLMs, but if you do for a little bit, you'll notice that new information propagates incredibly shallowly. So for instance, if you fine-tune a model that Taylor Swift has a new album, what you end up getting is that the model knows the name of the new album, but it doesn't update the number of songs that Taylor Swift has ever published. So it doesn't propagate information. Now, what we should have done is connected this more explicitly to behavior. We did a little bit where we basically say, under these interventions, models are going to change its behavior in this way. But I just want to take a little note about mechanistic interpretability, because this is something that I talk a lot about with students, and I feel like a lot of people care about mechanistic interpretability lately. And there's a lot of arguments about what mechanistic interpretability even is. I highly recommend, if you care about what mechinterp is, you read this paper called Mechanistic by Naomi Safran and Sarah Wigriff, two of my favorites.
Before you do that, can I ask you
Yeah,
a quickie?
of course.
I've been burning to ask this.
Go.
What do you mean by locate? I understand locate in space. I understand what locate in time means, but you seem to have a more general functional notion of, maybe you treat it as a space, but it's not a space.
That's a great question. And absolutely, this is something that we struggled to describe in the paper, and I honestly should have done more visuals here. So I'll mean two things by locate. The first one I want to talk about as time. Now, the LLM doesn't experience time, right? But it does experience different computational steps, at which place, its internal activations, which we can, vaguely kind of conflate with thoughts, are different. And so one thing I want to know is, at what point does the model have the information available to complete the relation, right? And what this says is that the model doesn't really have that information until the very final time step. So for instance, a lot of times you and I, when we answer a question, we know where we're headed with the answer. This doesn't appear to be the case with the LLM, so it can't precondition how it's going to write its answer based on the information it's about to say because it doesn't know it yet. The other thing is basically where, like, which literal mechanism, right? Because every layer of a transformer has different parameters. Which set of parameters actually stores that information so that if you wanted to edit that information and, for instance, change Twiggy to Brad Pitt, how would you do that? Well, as it turns out, what this basically tells you is you'd only have to change these parameters. And actually, that's what we're working on now. We want to make a way to just say, hey, without even training, I can make an update to these parameters that will change the name of this relation completion. And this mechanism, dynamic weight, or this technique, dynamic weight grafting, tells you which parameters you'd have to change in order to change that name, because that doesn't appear to be anywhere else, since the model can get away without any of the other weights being grafted in.
I don't feel like I've been cheated, but I don't feel like I've quite answered the question for myself that I asked.
So, like, yeah, go ahead.
When you answered in terms of time, it was clear. That was standard what we mean by localizing one way or the other. But there seems to be something else going on over here. And maybe what you mean by developing vocabulary is not just vocabulary for the users and the LLMs to use to exchange stuff among themselves, but something that the theorist can use in order to conceptualize this so-called space.
I mean, I totally agree. So, like, for instance, yeah, I don't have slides for this, which is too bad, but like these feed forwards, are made of certain mechanisms where, they go into a larger space and then they condense back down into the residual stream space. And we really do want to know, for instance, like we're doing an SV decomposition of these matrices and we're trying to see, hey, like, is the first, singular vector basically sufficient to update this mechanism, or does it have influences other than that? So we're literally looking at matrices and saying, ultimately, which numbers encode the fact that Twiggy is going to be the next name. In this work, we're doing this at a slightly higher level where like a feed forward is a few different matrices used in a certain way. And we just want to know, is this set of matrices the one that's remembering, or is it more diffuse? Because actually our first hypothesis was that it was way more diffuse and that it was kind of slowly built up over time. But this appears to be way less the case than we thought. There is some of that where if you, in certain cases, if you include a few more of these matrices, you can make the result stronger. But on average, you basically only need the matrices in these final, these like few feed forward layers at the end, which means that, let's say layers 17, 18, and 19 are literally where the memory is. And that if you swapped those out, for instance, in the fine-tuned model, it would no longer know the relation completion.
Okay, I don't want to interrupt more. You were about to say which components drive the recall pathway.
Oh no. So what I was going to say here was just about mechanistic interpretability in terms of uh, basically just zooming out. Mechanistic interpretability is this thing that people talk about a lot, and we don't have a good definition. And I'm not going to tell you what I think mechanistic interpretability is. I think it's basically a cultural definition. But I try to make an argument about, and your question is actually related to this. What do we want out of interpretability? And I would argue that what we want is, to answer one of the four questions or some combination of these four questions. Can we predict the model's behavior in new instances from the same distribution? Can we predict the model's behavior in new instances from new distributions? Can we predict the model's behavior on old instances under an intervention? And can we predict the model's behavior on new instances under an intervention? And I just want to highlight that the point of this kind of interpretability to me, it's always prediction. And so we should be like, when we think about interpretability, I don't really care whether it's at the neuronal level or whether you're just telling me whether a certain prompt gives a certain response. What I care about is how it generalizes. And I'm going to define generalization as my ability to make predictions in new environments. And so I just want to make this point where when I say I work in interpretability, I usually say I work in predictive interpretability because I do a lot of mech interp work. I mean, the like last 20 minutes were me talking about this mechanistic interpretability work where we look at neurons, we try to figure out what we could do with them. But what I cared about is what we could predict about them. And I think your question was exactly getting to that. When I talk about locating things, what I mean is what interventions will change the behavior and what won't. And that can either happen, in time step space or in terms of which parameters, which matrices I can swap out. And I think being able to predict what the new behavior will be when I swap out certain matrices is like a very good way to think about interpretability. But it's often interpretability is more about just so stories if we kind of forget that what we're really trying to do is predict information this way. So we have, I believe, something like, I forgot exactly. Oh wait, 30 minutes left. I have other things that I could say. But I first want to basically open up to questions because the other two like sections that I have are speculative, and I don't really mind if we do or don't get to them. So if anyone has thoughts about mech-interp or anything we've talked about so far, now is the time to open up for questions. All right.
Sounds like resounding silence. Go ahead.
Yeah, that's great. I'm excited to give you guys these things. So I now want to tell you, after all of that spiel, why mech-interp won't save your soul. So there's this quote from the beginning of basically this is the paper that invented mech-interp, which is literally called, oh, I forgot exactly, but I think, oh yeah, zoom in, an introduction to circuits. And it has the following quote. In this view, neural networks are an object of empirical investigation, perhaps similar to an organism in biology. Such work would try to make empirical claims about a given network, which would be held to the standard of falsifiability. And I love this quote. I think this is exactly what we should be thinking about when we think about LLMs and in general, neural networks as organisms to be studied. But I guess I have this question, which is why did this give birth to mechanistic interpretability when it applies just as much to behavioral science involving prompting? And so my core thesis is that if LLMs are organisms to be studied, prompting is behavioral science, and the behavioral science is useful. And to see what I mean by this, imagine that we had a bunch of aliens that came to visit the Earth, and we, tried to figure out what are these aliens? How do they work? How are they different? How are they the same? Well, you could learn a lot from surgery and from dissection, but I would argue you learn a lot more quickly by playing poker with the aliens, having conversations with them, and figuring out how you could coordinate with them. And that, we have this opportunity with LLMs, but because it's so easy to dissect LLMs, we're kind of tempted to do that all the time and feel that it's not rigorous until we can kind of, have some kind of essentialist theory that like maps things down to a certain parameter. And I call this the paradox of prompting, because prompting discovered nearly ever major LM capability, yet it's dismissed as alchemy. So for instance, like two things that I'm sure all of you guys know about LMs: in-context learning, where you show a bunch of examples and then have the LLM actually do the task, and then chain of thought, where you have the model think on its own in order to produce an answer. These are both literally discovered by people playing around with LLMs, saying, hey, what if I make this prompt slightly different? Finding an effect, and then saying, I can systematize what makes this prompt work, and I'm going to publish a paper about it. That's called the GPT-3 paper and the chain of thought paper. So why is it that everything that starts out as prompting gets rebranded? Well, I think there's a kind of social aspect to this, and this is kind of a cool, cute diagram for my paper, but I'm just going to give you a little taste of it here, which is that there's a difference between prompt science and prompt engineering. Prompt engineering is when people use heuristics that are poorly understood, and there's no rigorous attempt to understand them, usually in service of trying to make a system work slightly better. So it's when, you add a bunch of semicolons to a prompt because it turns out that increased, F1 from 30 to 30.5. And this is certainly something people do all the time, and it doesn't really improve science. However, exploratory prompting, followed by prompt studies to discover and confirm model behavior, is also something people do a lot of the time, but they often don't want to describe it as prompting and try to hide the exploratory part of this. I think there's this problem where in the scientific record, we tend to be ashamed to admit the exploration part of this. And I think that that's really bad when we're in this wild west of a new field and everyone's trying to figure out how to explore things. So you might say, okay, that's great. That's a cute little opinion, but what the question is an answer to? And I would say that science is all about resource management. You can see Chen Hao Tan's post in our Substack. And I say that, we have to decide what we're going to focus on and where we think the next breakthrough will come from, because we have to decide to fund certain projects. We have to decide to say, yes, I do want you to work on this, or no, I don't want you to work on this when we hire students or something. And I care a lot about how can we make the study of LLMs rigorous. And I think there's a very strong bias that the key to this is mechanistic interpretability. And even though I do mechanistic interpretability and I'm not against it at all, I disagree that this is the key. And so we made this diagram to compare mechanistic interpretability and prompting science. And our basic point is given most clearly through Mars levels of analysis. I don't know if you guys know, but it's like a hugely useful thinking tool. Basically, the idea is that there are kind of three levels to understanding a system. One is the computational level where we figure out what a system does, right? In the case of LLMs, it's actually very obvious in many ways. It's that it predicts the next token, but also obviously in doing this, it does a lot of other things, right? Like it has a map of personas, or it has a map of, politics, for instance, has been recently shown to be contained in LLMs, where there's an actual dimension corresponding to left versus right in the political spectrum. Algorithmic level ideas are more close to this kind of dimensional analysis, where we basically say, what are the algorithms by which the model implements the behavior that it does, right? What are the algorithms by which a system completes its purpose, completes its telos? And the implementation level is, okay, how do we actually make that happen with a neuronal system? What is it that this one weight matrix is doing? How does it shift the space in order to make this possible? As you can see, prompting science overlaps with mechanistic interpretability at the algorithmic level, but mechanistic interpretability kind of has a monopoly on the implementation level because it's very hard to look at implementation with prompting alone. But I would argue, and I think this is a hot take, that prompting science kind of has a monopoly at the computational level. And the reason why is that it's very, very hard to know what a system is doing from the bottom up, right? Like if I try to understand what the Earth is doing by just looking at the, rivers and the ecology and the animals, it's very hard to describe. In general, what we do in science is we get an intuitive theory for what models are, what something is doing, what a phenomenon is doing, and we model it. And then we say, okay, what are the parts that make this model act a certain way? And I think MechInterp is very, very good at doing that, but it's not as good at discovering what models are doing. And this is something that we care about quite a bit. So the kind of, at a practical level, I would say that prompt science is better at scaling because you can talk to any model in language, and language will probably continue to be the main UI of models. But MechInterp in general is very bad at scaling to larger models and different models. When it comes to scope, prompting usually has a very broad scope to the kind of problems you can study, whereas in MechInterp, you already need a very good definition of the specific computational thing that you're trying to solve in order to know how to study it. And at the understanding level, I think this is where MechInterp actually does win, where prompting science is better at giving people an intuitive idea of what a system does, but it is only really fully formalized when you actually have MechInterp tell you, okay, this is exactly what's happening. And if it wasn't, then you'd see this byproduct. And then I think, from the scientific narrative perspective, how does this fit into the rest of science? I think of it as prompting science should be for discovery, and MechInterp should be for confirmation and formalization, both of which are really important. But, since I've already put my cards on the table here, I think we have to be careful not to formalize too early. And I think that's a temptation we have because a lot of us, for instance, I was a trained computer scientist. We were trained to deal with systems that are a lot better understood. And so we're tempted to formalize to the extent that we could formalize old systems like programs, which, are also hard to reason about formally. That's what, PL and verification are about. But still, somehow language models are a lot more tricky to formalize. And so you might say, well, you like prompting more, so what? And I think the point that I want to make most is that we all secretly depend on prompting. And there's often a level of associated guilt, as if we should have a more principled way to discover how LLMs work, and we should just, plop something into the discovery algorithm, and then we'll see what the behaviors of the language model are, and then we can go and do our MechInterp, which will be very rigorous. But I think that we do too much of policing where hypotheses come from, and that actually playing around with something until it makes sense or until it breaks is a very scientific thing to do if you then describe under what conditions you were able to replicate this behavior. And I think we're very nervous about that because as computer scientists, we're not used to having to do exploratory rather than hypothesis-based science. But I think is absolutely the right time for exploratory science. And I think we need to start training people to do this more. Otherwise, it's something that amateurs and industry people will do, and academia will be kind of left in the dust. Now, to be clear, when I say left in the dust, I really don't want to train a language model on our own. I think a lot of people think that we should be trying to replicate industry's gains. I don't think we should do that. But I think we need to take in mind that in order to study a radically new thing, we need to take a radically different approach from what we were doing that wasn't doing as well in the last few years. And I think that's exploratory science, which is something that people have done for a long time, but it just hasn't been as necessary in computer science for a while because computer science is fundamentally a by design field. We usually make our systems and then we study them, and so we can control certain aspects of them. But it's hard to do that with LLMs because they're more grown than built or made. So prompting exploratory fieldwork and figuring out how to do this exploration better is useful and valid. And so I just encourage you to be brave about where your hypotheses come from and about doing exploration, because starting with a theory and then showing that the theory isn't that predictive can be useful if that theory is really obviously like the way things should work. But on average, I think exploring is often a lot more useful when faced with something radically new. Um, so that's the prompting a scientific inquiry section. I have one bonus section if we want, but now is a good time to stop for questions about whether you like prompting science or not, and why I'm so down on McIntyre, which I'm really not.
And I mean, I don't want to disappoint you, so go ahead, Dave. Take them.
I mean, I think I agree with you that prompting it's a reasonable thing to do and valuable thing to do. But I've just had like one kind of prompting science you described. Just one thing, maybe you said something about it and I missed it, but well, one thing I've been thinking, comparing these two things, is what do you think happens if the architectural basis changes, right? Because my intuition is that insights from the mechanistic interpretability will transfer better to new architectures if we ever get rid of transformers and attention and stuff. While those from the prompting side will not as much, right? And given how fast the field changes, it could be that we have a new architecture in a year and no one's doing anything anymore with transformers. And then, you would feel awkward to have a paper about prompting science that's specific to transformers, and while maybe the other thing transfers better. So I wonder whether from these, and you said it's about resource allocation, maybe from this is based on these assumptions, maybe it's more sensible to allocate the resources to mechanistic interpretability.
I think that's absolutely fantastic point. I'm so glad you brought it up. I wrote a paper specifically arguing against this thing, and so I highly encourage you to read it. I'll give you the upshot now, but it's called Generative Models as a Complex System Science. And yeah, I think this is the exact thing we have to worry about. And if it turns out that we think MechInterp is better for this situation, I think you're right. But my view about this is that actually I view it exactly as the opposite, which is that in general, I think most MechInterp work has been frustratingly specific to how we do things right now. And so that for instance, if we end up making models that don't rely on backpropagation, actually a lot of MechInterp work will not necessarily be valid. Not that it relies directly on backpropagation, but that it assumes things are continuous and it assumes certain kind of spaces, etc. Whereas prompting is something where if something is going to interact with a human, it will continue to use language. And, that in itself is a weak guarantee, though I think it is still a guarantee. I think the much stronger guarantee is that I don't think we're going to escape the general regime of density functions, where basically we say mostly we have unsupervised data and we want to mimic this unsupervised data. And so I think a lot of what prompting does is it tells us how we should discover various aspects of distributions or various subdistributions in a complex density function that we don't understand. An example of this that I really love is probably what I think the best LLM paper of the last 5 years. Embers of autoregression. Tom McCoy is the first author. I highly recommend it. I literally have it on my desk right here. It's one of my favorite papers. I always teach it. And the upshot from that is that because LLMs are trained to basically maximize the probability of the training corpus, they have all these predictable effects. So, one of my favorite ones is that LLMs can, decode sentences that use a Caesar cipher on, so like rot 13, where you rotate letters 13 letters forward in the alphabet, right? Um, but they're very, very bad at doing it for rotating 16 letters forward, because on the internet, rot 13 is very common, right? And so this is the kind of thing where I think they establish a few different effects, that the probability of the input and the probability of the output have certain predictable effects on how good the model will be at certain things. I think that kind of thing will remain true, right? If you like train a new density function. And so I think you're right. This is exactly the question that we should be asking, but I just fundamentally disagree with you about where the answer falls.
Okay. Yeah, I can see where you're coming from.
Did you say that you were going on to another module?
Yeah, I basically always have like a little bit of extra, so I have another module. But if there are more questions, I'm happy to open it up here. Then the next module is highly speculative, though I think people might find it interesting.
I want to hear the module, but can I ask you a very general question?
Yeah, please.
The idea of studying engineered systems as if they were organisms.
Yeah.
Let me ask you, how far can you push this? When a physicist is studying the universe, that's a natural phenomenon. When a
Right.
biologist is studying evolution, that is a process that's going on with, as you said, some elements, including
Yeah.
genetic elements on which it operates. Out of this came a phenomenon, a capacity, a human capacity, actually, a uniquely human capacity, which is natural language.
Yes.
How much of what you're saying to do with LLMs would apply to studying prompt science and prompt interpretability in human discourse?
Absolutely. I think that's a great question, and I actually want to show you like one of the slides that I showed in the beginning. Let me see if I can find it. Um, so this slide originally, oh, let's see if I can make this work. Here we go. This slide originally, I made it not to argue exactly about models, but to argue about the fact that we are thinking about humans wrong. I basically think that we should push it as far as we can. I think so. My One of the reasons why I went into academia instead of industry is because my ultimate goal is to create a theory of communication, and I just don't think this is on the minds of the people who at least in name nominally study communication, right? Where it's like there are linguists and they certainly study aspects of communication, but there's actually a lot less work on semantics than you'd think for linguistics. And the work on semantics is somehow very, very tight. Like I think, for instance, the best recent kind of effort in semantics is rational speech act theory, and it's very hard to export that from like something like a reference game. Now, actually, I think most human coordination is like a reference game, but it's often hard to describe exactly like a reference game because we don't have enough context. And so I actually think this is 100% true. This is the way we should be thinking about LLMs, or sorry, about people. And the LLMs can teach us a lot about how to study people. I think you can think about it as the following, which is that, you know, one of the reasons I think it's hard to, train like this is a little bit of a morbid topic, but like train better soldiers or make better weapons is because it's really hard to know what's going on outside of war. So for instance, this is why drones are suddenly getting so much better, is because they're being used so much in Ukraine that we actually know kind of what works and what doesn't with drones. The same is true with language, but with humans, we can't go and intervene about how language is used and what these specific things are. We can with LLMs, and they're not like I don't make any claims about how that they're like a second, a digital twin or something like that. I think they never will be. I think it's or never is a long time, at least for 100 years. I think it's too complicated. However, they're much, much more manipulable. And so, to the extent that they appear to kind of do many of the same things and at least be able to coordinate with humans, we can study human coordinations better with LLMs. And one of the things that I'm doing now is I'm making video games with LLMs where LLMs control the NPCs and where we can look at how humans coordinate in these video games. So I basically think this is how we should be studying human communication. I think behavioral economics, anthropology, linguistics, cognitive science, psychology have, they have pieces of the pie, but there hasn't been an impetus to make a general theory of communication. And if we were going to, it would come from studying behaviors at this level and trying to see how we could make predictive models of people and language use and coordination.
Communication or natural language?
I want communication because I think natural language is fundamentally a byproduct of communication. I take the Tomasello view that fundamentally for instance, syntax doesn't come, like syntax is somehow part of like the way our brains process language, and there's something I think inherent about that. I think there's significant evidence there. But the reason we learned to communicate as babies and the reason we did evolutionarily was use. It was because we could get certain things to happen. And that's one of the reasons why I think that communication is very fluid language is very fluid with other forms of communication, like dixis and gesture, like body language. I just don't think you can get away from the fact that these are part of the same medium. You can theorize about language in many ways much more easily because it's full of replaceable parts that we can study, using computational methods. But ultimately, I think it comes down to a real theory of this would have to be a theory of communication. If you tried to make it just about natural language, you would probably end up with something that's more form than semantics.
Okay, you've got 9 minutes left for your last module, so you better start it.
Let's do it. It's meant to be a 10-minute thing, and I'm sure I can be a little bit quick. All right, let's do this. So, articulating the ineffable, the case for AI-driven communication. So I'm going to take the AI safety point of view about this. Like, what are we scared of about AI? What aren't we? And this is the AI safety. We're going to start with the AI safety case for articulating the ineffable. And the basic idea of this is that we live in a landscape with increasing human-machine communication. And, that means humans talking to machines, machines talking to each other, machines talking to humans. And every time humans' environment changes drastically, it changes the way people think and deal with reality. My take is that LLMs will change the way people process their own opinions significantly more than the search engine, desktop publishing, and maybe even more than the university itself. So there are a lot of dangers to this. As people trust information from AI more because it learns to kind of pass the sniff test, it doesn't hallucinate as much. It's a way that we trust PDFs more than we trust, a JPEG, right? Like a JPEG can be manipulated. If someone bothered to make a PDF, they have a higher likelihood of being correct. And so people tend to trust PDFs more, which is kind of funny. This is a classic comic from KCD showing this idea. And overall, LLM deployers will find it easier and easier to manipulate public opinion en masse by just tweaking models for like certain things. Like, for instance, you could already imagine ChatGPT having a significant influence on whether people want to drink Pepsi or Coke. So what can we do about this? I think we have to help people articulate their own beliefs so that they're less likely to be manipulated, because once they've articulated their beliefs, they're less likely to change them. And there's a bunch of evidence in psychology under the term inoculation theory to support this. And the way LMs can do this is we can reduce the costs associated with taking the time to articulate beliefs and get them wrong and try to get them right. So we can make the time shorter. We can make the social risk shorter because, misarticulating your own beliefs with another person has higher social risk. And we can reduce the opportunity cost, right, by basically saying, well, I didn't waste that much time or energy or money doing this. And the upshot of this is that, here's my view of people. There are currently articulable beliefs, which are this tiny little crust on top. There are the truly ineffable, which is a really significant portion of humans. But in between, there are a lot of other things. There are the untranslatable cultural truths that we get by being immersed in a certain culture. And there are things that are ripe for the picking, which are actually, expressible across culture and haven't been articulated yet. And that's what I want to focus on. So the benefits to this are, let's say, twofold. So there are many ways we could break this up. One is that articulated beliefs are in general less manipulable, and we have actually significant, a theory and empirics to back this up. Now, I want to acknowledge immediately a counter argument, which is that articulated beliefs are also more manipulable on articulation. So if I hint to you how you should articulate a belief, then actually I can manipulate it, the articulation of it. And then once you've said it out loud, you're likely to believe something that you didn't actually believe before. So this is kind of a complicated situation, but at least presents a possible benefit. Number two, which is something very close to my heart, it's probably the thing that I care about most in terms of social, order and like caring about people, is that we want to get rid of the hidden curriculum. Then we need to make tacit knowledge accessible, cultural baggage and all. So for instance, we made a video game about this, which basically has you ghostwriting for an HR manager, and it kind of exposes the different ways in which American corporate culture forces you to act and what the underlying dynamics and games people play are. And I think these kinds of games are way better at expressing this than something like, there are books written about this. Like, for instance, I highly recommend the book Moral Mazes for those of you who are interested in the sociology of American corporate culture. I just had my entire lab read it. It's a really interesting take. But people aren't likely to read these things. They are likely to play games, and games are better at expressing the pressures in a system than an equation or people are in terms of making it accessible to a wide variety of people. And if you want to play our game, take a picture of this QR code because I think it's pretty fun and I think you'll kind of have a blast seeing how we show what American corporate culture is like. But I also want to acknowledge that there is absolutely a human danger case against articulating the ineffable. One is that if people know what they want, then people will choose not to interact with each other. And we've already seen this with the really rapid rise of AI romantic partners. This is from Replica. But there are a lot of these. And basically, I think the most recent survey is that globally, there are, somewhere around 10 to 20 million people who have at least weekly romantic kind of engagement with an AI, which is an incredible number of people. I mean, it was essentially zero until like a year or two ago. So this is a dangerous thing. I don't think we know how to deal with a society where people don't meet each other, right? And, romance is not the only way of meeting each other, but it's a big one. Another danger is that if people know what other people want, then people will no longer be able to use ambiguity to harmonize. Or as Jean-Paul Sartre said, tell is other people, right? And so to illustrate this, I want to tell you about the social Leidenfrost effect. First, the Leidenfrost effect is where, if you cover your hand in water, you can actually kind of push it through magma. And if you're really quick, you won't get hurt at all. And do not try this at home. This is not an endorsement because basically the magma will first burn the liquid on your skin. And in the time that it takes to evaporate, you'll already be out of it. So I would argue that there's a social Leidenfrost effect, right? Where, for instance, we use ambiguity, like as this kind of vapor or this liquid in between. So, a father telling their child, you wouldn't drink at a party. And then, the son says, of course not, dad. And this keeps a shared fiction that there will not be drinking at this party. And this father is overall happy and is somehow preserved from this knowledge that would hurt him. I think this is a very common occurrence in society. And pretending that we live in a society of radical honesty is not helping anybody. So I also think that kind of to end here, hermeneutic competition is something we have to care about a lot. Understanding is a limited resource, and not everyone can be perfectly understood by everyone else. So as we use LLMs to help us mediate who can express themselves and who is heard, we have a lot of hard decisions to make. So, who understands who is influenced by where you grew up or how you use social media. But now there's a new potential influence, which is what do LLMs find easy to talk about and what feels like pulling teeth? If LLMs find something easier to talk about, it'll be more commonplace knowledge for people. And so people who experience that kind of thing will find it easier to talk about it to other people. So any notion of how LLMs ought to be has to reckon with the fact that LLMs shape expression, and thus who can explain themselves to whom. This is often called hermeneutic injustice, when someone's ability to understand or communicate their own experience is undermined due to gaps in collective interpretive resources. And inevitably, there's going to be competition for who becomes understood versus who is left misunderstood. And so I just want to say the struggle to decide the playing field of human expression is already in full swing, and LLMs are a big part of that. We, as people who use LLMs and who study LLMs, have to think about what influence we want to have. And with that, that's the end of the presentation. So I'm happy to take questions. I'm even happy to take insults, but I don't take comments.
You won't be able to have questions, unfortunately. We just have 1 minute left, and the only thing I can say is that your enthusiasm is contagious, and the interesting thing is that it's contagious both on the points that we agree with you about and the ones that we don't agree with you about.
That's the best possible result of a talk. So fantastic to hear it, and thank you so much for having me. It was a pleasure.
How's the weather in Chicago? Are you having all of this stuff?
I'm having a very, very dreary kind of time. I don't know if you can see it. Yeah, exactly. So it's about there.
Well, thank you for taking this virtual trip to Montreal. Make the next one real.
That sounds like a plan. Thank you so much, Stefan, and thank you everybody for joining. It's a pleasure, and I'll see you in Montreal sometime.